Hello everyone, welcome to trigonometry. According to the way our textbook is written, the traditional starting point of trigonometry is chapter 6, and that's where we're going to begin. By the way, our textbook is Pre-Calculus by Stewart, Redlin, and Watson, and this is a pre-calculus book, not a trigonometry book. So it contains both the college algebra materials and trigonometry materials in a single volume. If you had college algebra with me, then you'd have used the same textbooks, so you must already know. Now, the first 4 chapters concern college algebra, 1, 2, and 3, and 4. And then chapter 10 also belongs to college algebra. Now, where do we begin? Chapter 5 or chapter 6 both talk about trigonometry, and it's a little bit puzzling. Now, I haven't had a private conversations with any of the authors, so I cannot say this with 100% certainty, but I think chapter 5 was intended as a part of college algebra materials rather than part of the next sequence. The reason is because there are so many overlaps in chapter 5 and chapter 6. They talk about the same topic in 4 different viewpoints with all the same conclusions and for same techniques. What's the point? I mean, there are so many of them that it's really bothering me. Now, if I assume chapter 5 as a previous sequence course, then it makes a lot of sense because naturally any instructor will have to do a lot of review in the very first chapter of the next sequence course. Then everything dissolves okay. So that's the assumption I'm going to base my syllabus upon. I'm going to start from chapter 6, but I will use bits and pieces of chapter 5 as supporting materials. Okay, let's begin. Chapter 6, trigonometric functions, and we're going to begin with angles. But before that, let's talk about some notational issues. Here we have a nice picture, and the angle is represented in a Greek letter theta. We're going to use Greek letters, theta most often, or alpha and beta and things like those for radian measure of the angle. What is a radian measure? Please be patient, we're going to talk about it in a moment. Now, Greek letters are sometimes difficult to typeset, so I may use theta for T for theta, A and B for alpha and beta, and so on. But in any case, and whenever possible, I will use Greek letters for radian measure. By the way, I'm going to use capital A, B, C in Romans for degree measures. Degree, minutes, and second measure, which is also called DMS measure. Okay, we talked about the notation. Let's begin angle. Now we have 2 pictures here, figure 1, and both show the angle behavior. Both have a black ray OR1 and blue ray OR2, and black is labeled initial and blue is labeled terminal. What are we looking at? We are looking at rotations. The black ray OR1 is the initial ray, and if we rotate it with respect to the origin O, then we are going to end up with a blue ray OR2. Now the first picture of figure 1 shows counterclockwise rotation, which we call positive angle, and the second picture shows clockwise rotation, and that's going to be the negative direction. It's kind of like moving right versus moving left in a number line. In a number line, in real number line, moving right is positive and moving left is negative, isn't it? Likewise, in rotation, counterclockwise rotation is positive, clockwise rotation is negative. Okay, we talked about the sign of angle measurement, so let's now talk about the magnitude. We're going to use radian for magnitude, and 1 radian is defined as the arc length, or more precisely speaking, counterclockwise arc length divided by the radius. And we have 4 pictures in figure 3, and first picture shows 1 radian. So the arc length, the counterclockwise arc length, is the same as the radius. So that ratio is 1. That's 1 radian. The second picture, Now we went half circle, and the counterclockwise arc length is half circle. What is circumference formula for the circle is 2 pi r squared. Oh no, excuse me, 2 pi r. 2 pi r, and half of that is pi r. Now divided by r, I'm going to get pi. So we have pi radian. And then let's go over to the third picture. This time it's half of pi, and that's 90 degrees. So 180 degrees was pi. 90 degrees must be, well, half of pi. Kind of like that. That's how we measure the radian angle. And the conclusion is, our textbook author is withholding the conclusion. More and more. Well, here it is. Angle theta is measured. Angle theta is basically S over R. S is the arc length, and R is the radius. But that's when we discuss only the magnitude. If you include a sign, the S can be either positive or negative. Counterclockwise arc length is positive, and clockwise arc length is negative. And that's how we get the angle measurement in radian measure. Theta is S over R, including the sign. And of course, if you throw away all these signs, pluses and minuses, and then algebraically manipulate, multiplying R to both sides, then we're going to get the previous formula, S equals R theta. And that's how we can find out arc length from the central angle and the radius, if you have radian measure. Well, has it been sufficient explanation? Well, that's the way our textbook does, but I'd like to have a little bit better explanation than that, and also I'd like to have a little bit more freedom to write down and highlight. So let's move on to the notebook I created with Mathematica, and then let's talk about radian angles in several different viewpoints. And first, let's talk about it in the unit circle. Primary reason is for simplicity. This is an equation of a unit circle. X squared plus y squared is equal to 1, and there you can see explanation. X is horizontal of this inscribed red right triangle. Y is vertical. So if you use Pythagorean theorem, horizontal squared plus vertical squared is hypotenuse squared. So you're going to have actually 1 squared. Radius is 1. But then again, 1 squared is equal to 1, so we have just 1. This program is randomized, so you can run it again, and then you're going to get some different point on a circle. This time, x is negative. But does it matter? No, because we're going to take square anyway, so x may have been negative, but x squared, that's the same as horizontal squared. No problem there. In this case, x is positive, but y is negative, but it doesn't matter because I'm going to take square anyway. Now, here is the visualization of the radian measure, or radian angle, on a unit circle. It's the same as counterclockwise distance of motion starting from the initial point to the terminal point, or counterclockwise arc length. This program is randomized, so you can try various things. If you move backward, that is, if you move clockwise, then the angle is negative. You can also see the periodic behavior of the angles, kind of like these. The first picture you're looking at is just plane rotation about theta, where theta is between 0 and 2 pi, between 0 and 360 degrees. The second picture you're looking at is theta plus 2 pi, so you just go over to 360 degrees, back to the original, and then once more. And in the end, we end up with the same ray, same terminal point, so we are looking at the same angle. Excuse me, what am I talking? We're looking at different angles, yes, but the same terminal point, same terminal ray. What if we go backward? Well, The first picture is showing you just theta rotation, and the second picture is showing you 2 pi minus theta, 300 degrees minus theta. So we are going backward, but we end up with same terminal point, same terminal ray. Now, that was a good visualization, but not general enough. This is a little bit more general case. We can do the same thing in an arbitrary circle centered at the origin with radius r this time, not just 1 but r. So what do you have? Inscribed circle looks like, inscribed triangle, excuse me, looks like this. X is horizontal, y is vertical, and r is hypotenuse, so hypotenuse is now r squared. By Pythagorean theorem, we have that, of course. This program is randomized, so if you run it again, you're going to get different terminal point. In this case, both x and y are negative, but doesn't matter because we're going to take square anyway. In this case, x is negative, y is positive, but we're going to take square anyway, so no problem there. How about the angle? Well, this is nice. This program is randomized, so you can run it again to have different radius, different radii, and different angles. And the outer circle is fixed as radius 1, and the inner circle changes. I said it changing between 0.25 and 0.75. And as you can see, we have different circumferences, but if you divide by radius r, then we have the same terminal result, and that's what you're looking at, the angle. If you go backward, it's the same situation. Oh, this time we got something pretty close to negative 90 degrees, negative 0.49 something, so that's pretty close to 90 degrees. In the end, what we get? Arc length over radius is the way we define angle. And the arc length actually has sign, positive direction and negative direction. So counterclockwise we have positive, clockwise we have negative. So theta is S over R, and S is R times theta if you manipulate algebraically. If you throw away all the signs, if you look at only magnitude, you can use the same formula too, except that this time we are taking only positive values only, no matter what direction we move. But that's useful for geometry. However, that's not the definition of the angle. The definition of the angle is right over here, arc length over radius, or more precisely speaking, counterclockwise arc length over radius. Now let's talk about the relationship between radian angle and degree measure angle. DMS angle and radian angle actually measure the same quantity except for different unit. So all I need is conversion factor. Kind of like multiplying 1.6 something to change miles to kilometer. And well, multiplying by, let me see. Oh, I forgot the other. Multiplying by 0.45 approximately to change pounds to kilogram. Likewise, the conversion factor is pi over 180 degrees for the MS angle to radian angle. As a matter of fact, this notebook is not entirely correct, to tell the truth. I should have kept this degree sign. So the MS angle is given as degree. So after cancellation, we have to lose that degree. Okay, these are a bit, yeah, okay, here's a better example. 65 degrees. How can you express this one into radian? Well, 180 degrees and 65 degrees, they cancel each other, and then we end up with pi times 65 over 180, and then after plugging pi is approximately 3.84, we get radian measure. Please note that we have degrees and degrees canceling each other out, and then we usually gain pi. Kind of like this. Degree cancel out, and then 30 over 180 is 1/6, and we gain pi. So that's the way we convert degree to radian. We can go backwards to radian to degree, simply multiplying by its reciprocal 180 degrees over pi, and then we can convert radian measure to DMS measure.